Our goal for today is to talk about what happens if we ever run into a situation where, for whatever reason, we can't find antiderivatives. Because we oftentimes think of like, oh, integration is just finding antiderivative. Well, that's one way to approach integration, and that's using the fundamental theorem of calculus. But there are other options out there. And so we want to look at one of our options, which is numerical integration, which is a way that we can get the answer, or rather a reasonable approximation to the answer, by using techniques where we break things into parts and add them up. Who would have thought that we'd do that for integration? So let's begin. So what's going on? Well, like we said, look, if you have the fundamental theorem of calculus, great. But there are functions out there which have no nice antiderivative. Now I want to be careful here. When I say no nice antiderivative, it doesn't mean that it doesn't have an antiderivative. It just might be one that we can't express in a nice way. As a very simple example, e to the minus t squared. It's a very reasonable function. In fact, the further you go, you say, oh, this is not just a reasonable function, it's an important function. If you look at the graph of e to the minus t squared, it has a nice shape. It looks something like this. And this is sometimes called the bell curve. And it plays a big role in statistics. And so we'd like to be able to say stuff about, well, how much area is there underneath this curve? And so statisticians actually have big charts and tables full of this data out there. Of course, nowadays, it's all stored in a computer. But we can't find the answer to this question by saying, oh, here's the antiderivative, and just evaluate. So we have to come up with other methods. So that's one thing that can happen, is that we have a function whose antiderivative we don't know. But in fact, there can be a more fundamental problem, which is we may not know the function. So you can imagine that something might happen where it's like, okay, so there's some curve, but we're not given a formula for this function. Or oftentimes, and this is something you see out in the world, is we don't even have the curve. What we have are a series of points. In other words, we've sampled something here. So we have not a function, but rather sort of bits and pieces of information about a function by saying, well, here's what it's doing at certain times. And we don't even know what it's doing in between the times that we've sampled. Who knows? Generally speaking, we make an assumption it should do something reasonable. And so we say, well, look, if we're in this situation where we have an unknown curve, or if we're in a situation where we have sampled data, what can we do? We definitely can't apply our fundamental theorem of calculus because there's not a function to work with. So we say, look, we know what integration is about. Integration is about breaking things into parts and adding them up. So even if we don't know the function exactly, we can say, well, look, we'll still break it into parts. We'll look at what's happening with each part, and we'll add the parts back together, and that'll give us our answer to a reasonable approximation. So our goal, we're talking about numerical integration, is getting sort of a number attached to it. And we're going to stay at the start here. Look, we're not after being precise. We're not after the exact value. We're after great estimates, very good estimates. Well, let's start with something that's probably a little bit familiar. And what we're going to do is we're going to say, well, break things into parts we know. So the thing that we know really well are rectangles. So we're going to think of saying, okay, the small thing we've broken up into is rectangles. So we've got lots of little rectangles stacked right next to each other. And we want to find the contribution from each rectangle. So we say, okay, what is this? Now we've done this before. When we first started talking about integration, we talked about Riemann sums. So this is really just a review of Riemann sums. And what we say is, all right, the contribution from each piece, we're thinking of it as a rectangle. Well, that's going to be the base times the height. So the base, that's our change from our left to right endpoint, xk plus 1 minus xk. You might also think of this part right here as being our delta x. In other words, our change in x. So we say, great. So what we can do is say, well, what's the height? Well, here's where we can make a choice. So you can choose, if I'm going between xk and xk plus 1, I can pick any point in between here and use that to figure the height. So what we'll do is we'll pick a couple of easy candidates. We'll say the left point, so this is xk, that would be a left rectangle. We call it the left rule. And then there's the right endpoint, so we'll call it the right-hand rule. And then, of course, there's the middle point. We'll call that the midpoint rule. So what does that say? So the left point says the contribution is take the function at the left end of that interval, take the function at the right end of that interval, and the midpoint, take the function at the middle of that interval. And that's the height. So again, we're showing each one of these is a rectangle, and we're approximating the area of each part. Now, there are some definite pros here. It's pretty easy to work with. There's some definite cons, not very precise. You can see here there's a lot of missing area. It's a little bit better for the midpoint, but still, there's a lot of parts missing here. So it's not the most precise. And when you're dealing with sample data, it's also, in some sense, the most unrealistic, because it says, look, my function is sort of flat, and it almost behaves like, like the robot dance. And that's not how we think functions should behave. They shouldn't be jumping up in this step-like fashion. All right, so now what we're going to do is we're going to say, okay, instead of thinking of it as a rectangle, let's change our mindset a little bit. We can say, well, we're thinking of the top as just a constant function. So what's one step up from a constant function? And the answer is a line. So the next thing is we're going to think of the trapezoid rule. And what we're going to do is we're going to say, hey, now what we're going to do is think of trapezoid shapes. So you have two parallel sides, and the bottom, you got a nice little square shape here. And then one side comes at a sort of a sliced angle. And the area of a trapezoid, it's given here, you average the heights times the base. So what are we going to do? Well, if we have a curve, so here's our curve, and what we can say is, look, we'll take the area is the area of the trapezoid, 1/2 the height of the function at the left end, the height of the function at the right end, times the width. So the area of one trapezoid is this expression. So 1/2 f of xk plus f of xk plus 1 times our width. This is our delta x. And now we add it up, and that gives us an approximation for our total area. And so we say, great. That gives us a nice way to approach it. Now, if you think about what's happening here, we say, hey, the trapezoid rule is doing what? Well, you could really write this if you expand on this plus sign here. This is 1/2 the sum f of xk delta x plus 1/2 the sum f of xk plus 1 delta x. So remember, this is our delta x. And this right here says, oh, you're using the left-hand endpoints, and on the other hand, this part is using the right-hand endpoints. And so it's, in some sense, it's sort of averaging out halfway between left and right. So that's the trapezoid rule. By the way, I'll just point out, how can you get this formula, 1/2 h1 plus h2? Well, one way you can think about it is you can think of it as doing the following. You go to the middle, and you say, look, let me go up here. And now what we'll do is we'll say this triangle part right here, you can flip it over and it exactly fills that hole. So this will exactly fill that hole. And now we say, okay, so it's a rectangle. The base is still the base. And now, what's the height of the rectangle? Well, it's the average of the two heights. So that's where you get the 1/2 h1 plus h2. All right, so it is feeling better because we were saying, oh, look, our pieces are behaving now like straight lines. So now it's not just a, doom, doom, doom. It's straight line segments. But you might say, can we do better? And if you think about what happened, okay, so when we think Riemann sums, our top is behaving like a constant function. When we're saying trapezoid, it's saying, ooh, make it behave like a line. Well, what's the next step? Where do we go? And the answer is parabolas, right? Because that's constant is a polynomial of degree 0. Line, polynomial of degree 1. So parabola, polynomial of degree 2. So here's the idea. Now it's a little bit more interesting. And what we do is we say, look, instead of having one strip, we're going to actually look at pairs of strips. We'll get into why. Essentially, if you think about parabolas, if you think of it as like ax squared plus bx plus c, that says there are 3 pieces of information, those coefficients a, b, c. So what I want to do is I'm going to say I want to match at 3 points. So that's why we want to take 3 points. And so that's 2 strips. So there's xk to this middle point, which is xk plus 1, then xk plus 1 to the xk plus 2. So we're going to find the parabola that passes through those 3 points. And it's actually marked here with this dotted line. Now the thing is, in that picture, it's hard to spot. Is there a difference? Well, because parabolas are even a better approximation than lines. So this is a zoomed in picture here. And if you look, there's just a little teeny tiny sliver of difference. Here, the parabola is a little bit over, and over here, it's a little bit under. But just barely. So it's very, very close. And it's a much better approximation. So it does a better job of capturing the behavior of the function. Now, here's the thing. There's a slight trade-off in that it gets a little bit more, I'll say, interesting to keep track of what's going on. So, when we think about the area under the parabola, well, if we pass through our left, middle, and right, well, it turns out it's 1/6 f of xk plus 4 f of xk plus 1 plus f of xk plus 2 times xk plus 2 minus xk. So that's the area of the parabola that passes through those 3 points down to the axis. All right, so that's what we have. So you say, oh, well, what does that mean? Well, if you look, it's saying there's the left hand, the right hand, and the middle point. And if you look, it says, look, the midpoint is much more informative. It's weighed a lot stronger. And so you can think of Simpsons as being some sort of this weighing of left, right, and middle. All right, well, great. So how does this work? Now you have to be a little bit careful here. Now, the reason we have to be careful is Simpson's rule works by taking pairs of strips, 2 at a time. And so we start by saying, all right, we're going to break up our interval going from x0 to xn. N has to be even. So n is how many strips you have. Now, we're going to think of consecutive pairs, and over each consecutive pair, we're putting a parabola on top. And finally, we say, okay, apply this rule for each pair. what we end up with is the following. We get b minus a, so that's from a to b, over 3n. Now, what's happening here is this assumes, and when we're doing numerical integration, we make this assumption, is that we break up evenly. Now, technically speaking, you don't have to break up evenly, but almost always we will make that assumption. So that says that the width of each interval is equal. So what is the width? Well, if we're going from a to b, then if you think about it, it's b minus a over n. That's the width of one interval. So now you have a b minus a over n. You might say, well, where does that 3 come from? We'll get to that in a second here. All right. Now, how does it work? Well, it says f of x0 plus 4fx1 plus 2fx2. The next one would be 4fx3, 2fx4, so forth and so on to the end. In other words, the coefficients have the pattern. If you look at these numbers in front, 1, 4, 2, 4, it follows the pattern 1, 4, 2, 4, 2, 4, 2, 4, and it'll end with 4, 1. Where is that pattern coming from? Well, what happens is when I look over 2 consecutive intervals, I'm looking at 1, 4, 1, and then the next consecutive will be 1, 4, 1, but notice that the 1s line up. So you'll end up with a 1, 4, 2, 4, 1. But of course now this will also have an overlap where that 2 is coming from. So really it's a 1, 4, 1, and then on top of that is a 1, 4, 1. So these 2's are that coming together. You get that double counting coming into play. Where did this 3 come from? Here's how I like to think of it. What we're really doing is we're saying, look, we're going to, for each 2 strips, so there's 2 strips, I'm going to look at 6 pieces of data. I'm going to look at the left hand 1 time, the right end 1 time, and the midpoint 4 times, getting us up to 6. So we read off 6 pieces of data to cover 2 strips. Well, that says, look, we should divide 2 by 6. So that's where that 1/3 is coming from. 2 strips, 6 pieces of data. So that's why we need to have this compensating factor of 1/3. By the way, we should have pointed this out for the trapezoid rule. It's very similar. If you write down what happens here, you could say that the trapezoid rule becomes b minus a over 2n, and then it's f of x0 plus 2f of x1 plus 2f of x2 plus 2f of x3 and so forth, plus 2f of xn minus 1 plus f of xn, and the coefficients are 1, 2, 2, 2, 2, 2, then 1 on the end. And then what's really happening is you say, look, for each strip, I'm using 2 pieces of data. So 1 strip divided by 2 pieces of data. That's where this 2 is coming from in front. Why is it 1, 2, 2, 2, 2? Well, again, 1, 1 next to a 1, 1. The overlap is what causes the 2. And then again, more overlap all the way down. So that's another way to write down the trapezoid rule. All right, now, where did this come from? Well, we're not going to derive it, but we will verify it. So we're going to do a quick verification, and, well, depending on what we mean by quick. So here we go. We need a couple of facts, namely, look, if I have a squared minus b squared, it's a plus b, a minus b. So that's the difference of squares. You can also do difference of cubes. A cubed minus b cubed, a squared plus ab plus b squared times a minus b. And now, what do we want? Well, we want to say, look, I have this parabola, ax squared plus bx plus c, and it's the one that's best approximating my curve. Okay, well, what does that say? Well, it's the one where what we have is we have our 3 points, x, k, xk plus 1, xk plus 2. Whoops, there we go. Imagine those are equally spaced, and we have our 3 data points. Okay, so we have those 3 data points for this parabola, and there is some unique parabola that will pass through those 3 points. One does exist. And so we have such a parabola, and we say it's this one. This is the right parabola. Now we say, look, we need to figure out what's this area. So that's our goal. How do we find this area? Well, you integrate from xk to xk plus 2, ax squared plus bx plus c. Well, we know how to integrate parabolas. 1/3 ax cubed, a half bx squared, and cx, and evaluate. And so, all right, so 1/3 a, then it's the top, xk plus 2 cubed minus the bottom, xk cubed, a half b, the top, xk plus 2 squared minus the bottom, xk squared, and then c times xk plus 2 minus xk. Now, we say, look, this xk plus 2 minus xk, we'll call that our delta x, and because of the difference of squares and difference of cubes, this has an xk plus 2 minus xk, and this has an xk plus 2 minus an xk, and we pull everything out. So we get this wonderful expression here, 1/3 a times xk plus 2 squared plus xk plus 2 times xk plus xk squared, a half b, xk plus 2 plus xk, and c. All right, there we go. Now, the fun part. Well, like we said, we know this parabola passes through those 3 points. So that says if I plug xk plus 2, or the midpoint, which is halfway in between, that's our xk plus 1, then we're going to say, look, f of xk is what happens when you plug it into the parabola, and with xk plus 2, and with the midpoint. So the last thing to do is say, all right, let's actually combine these together. So we're going to multiply the first one by 1, the second one by 1, and the midpoint by 4. Right? Left times 1, right times 1, midpoint times 4. And when we do that, what do we get? Well, we're going to get the first one. We're going to get the 4 times the middle one. See, that's multiplied by 4. So that gets rid of the 1/4 times 4. A half times 2. Sorry, a half times 4 is 2. And 4 times 1. So there's our midpoint. There's the right end. And now we just group everything together. And we say, well, what happens? Well, as far as the a's go, we get what? There's an xk squared. There'll be another xk squared. So there's 2 xk squareds. There's a cross term, which would be 2 times xk plus 2. So that's where that term comes from. And then there's an xk plus 2 squared and another xk plus 2 squared. Perfect. And then similar with b. We get a b times xk, and then there's a 2bxk. Here's a bxk plus 2 and a 2bxk plus 2. 3b times xk plus 2 plus xk. Then a c, a 4c, and a c, 6c. And now it really comes down to saying, hey, compare this piece to that piece, and what do we see? Well, we see they're off by a factor of 6. So if you multiply this by 6, then you get your 2a times that term, 3b times that term, and 6c. So multiply this by 6. We need to divide by our delta x. And now we say, lo and behold, multiply by 6, divide by that, and we get our area. So now we say, perfect. We want to solve for area, and therefore we get, if we move this across, our area is what we claim it is. 1/6, the function on the left, 4 times the function in the middle, plus the function on the right, times the width from beginning to end. And we're done. That's it. That's the justification. Now, you might be wondering, hey, if we can do better with the parabola, why stop there? Can we go further? Can we go cubic? And the answer is yes, you can. And what it is there's something called Simpson's 3/8 rule. And it says the following. It says, look, if you want to approximate by cubic, what you do is you have 4 points. Because a cubic, you have ax cubed plus bx squared plus cx plus d. So you have 4 degrees of freedom. And so what we do is we're going to combine 3 consecutive intervals. So we have 3 consecutive intervals. All right. So we have our xk plus 1, xk plus 2, xk plus 3. And now we have those 4 data points. All right. Well, there is a unique cubic which will pass through those 4 points. And we can sit down and say, okay, what's the area of that unique cubic which will pass through those 4 points? So we're looking for the cubic that does something, I don't know, something like that. It's hard to spot it right away, but okay, what's this area? And it turns out it's found by the following. 1/8 of the function on the left, 3 times the second term, 3 times the third term, and the function on the right. And so we say, great. Well, now where does this 3/8 name come from? Well, for every 3 intervals, I'm going to read off 8 pieces of information. Because I'm going to read off 1 plus 3 plus 3 plus 1. So 3 over 8. That's where the 3/8 comes from. And now you can write down the pattern, right? Because what do you see happening? We look at it, we say, look, there's a 1, 3, 3, 1. And then the next set of 3 will be a 1, 3, 3, 1. But they overlap so that if you look on the left end, that's going to match up what's happening with the, if you look at what's happening with the right end, that'll match with what's happening on the left end. They overlap. So it's going to be 1, 3, 3, 2, because of the overlap, 3, 3. And then it keeps going. So the formula, the 3/8, because for every 3 intervals, I'm going to use 8 pieces of information. Then there's the b minus a over n, which is the width of every interval. And then you're going to follow a pattern. And the pattern is 1, 3, 3, 2, 3, 3, 2, 3, 3, 2, so forth and so on, up until the end. It's going to end with a 3, 3, 1. So it's a little bit harder to remember. F of x0 plus 3f of x1 plus 3f of x2 plus 2f of x3, and so forth and so on. And at the very end, you have an f of xn. Notice that in this case, you have to have that n is a multiple of 3. And you can keep going. You can get more and more information, and you can fit more and more data. Now, we're going to stop at just normal Simpson's rule. We're not going to use the Simpson's 3/8 rule. I'm just saying that it exists. And you can use better and better approximations. But at some point, there's going to be a trade-off, because you can do something called overfitting, which is you can say, well, perfect. If I can, find a cubic that goes through 4 points, well, look, if I have 100 points, here's my data, then I'll just find a polynomial of a degree 100 that passes through all those points. Actually, I only need a degree 99, but all right. Is that a good idea? And the answer is no. Because what happens is you might have something that looks like this, but if you find a high degree polynomial, it could be doing some really crazy stuff in the middle. So even though it seems reasonable to try a high degree polynomial, in order to fit all the data, it might have some very wild oscillations in between your data points. So there definitely is a trade-off. And at some point you have to say, look, I'm losing by trying to do too much here. So for most applications, the Simpson's rule is about where we stop. We say we're pretty happy with that. And so actually, since I guess that's where we stop, it's a great time for us to go do some work And we're done for now. All right. See you soon.